In 1928, a young physicist named Paul Dirac walked onto a stage in Germany to present a new paper. His presentation was detached and quiet, but the mathematics he shared sent the greatest minds in quantum mechanics into a panic. Werner Heisenberg wrote to his colleagues in despair, calling the theory the saddest chapter in modern physics, and Wolfgang Pauli allegedly threatened to abandon quantum physics entirely to write utopian novels instead. Their reactions stemmed from a single, impossible outcome. In Dirac's work, his math clearly predicted the existence of a particle with negative energy. In classical physics, energy below zero cannot exist. If an electron could drop into a negative energy state, it would continuously emit photons, radiating away infinite amounts of energy as it fell endlessly into a bottomless pit. The math described a universe of absolute instability. If negative energy was a physical reality, all matter should have immediately collapsed on itself. To understand how Dirac arrived at this crisis, we have to look at the two pillars of early 20th century physics. The first was Albert Einstein's theory of special relativity, which dictated the laws of physics for anything moving near the speed of light. And the second was Erwin Schrödinger's new field of quantum mechanics, which used wave equations to describe the probabilistic behavior of subatomic particles. The problem was that these two pillars were completely incompatible. If you applied Schrödinger's equation to an electron orbiting a heavy atom at near light speed, the math broke down. This is a visualization of a standard wave function. Several physicists tried to merge these theories by plugging Einstein's relativistic energy relationship into a wave equation like this one, but their math relied on a second-order time derivative, meaning the wave function was differentiated twice. This resulted in an equation that output negative probabilities. A probability of less than zero is physical nonsense. The scientific community was stuck at an impasse, forced to choose between the rules of relativity and the rules of quantum mechanics. Combining them produced a reality that couldn't exist. Dirac approached this problem with a highly specific philosophy. He believed deeply that a good theory must possess inherent mathematical beauty, and that elegant equations were more important than matching current experimental consensus. To bypass the impossible negative probabilities, Dirac set out to invent a linear equation. If he could keep the time derivative to the first order without squaring the energy operator, he could unite the two theories cleanly. But when he expanded the momentum into 3 dimensions and tried to solve for the coefficients, he hit an algebraic roadblock. Using standard numbers like 1 and -1, the equations produced contradictory results, always outputting either -2 or +2. The math only worked if the order in which the variables were multiplied changed the final answer, just as reflecting a vector across an axis and then a diagonal gives a different outcome than doing those steps in reverse. His coefficients required a directional sequence. By trusting these abstract mathematical concepts over intuitive logic, Dirac proved that the foundational laws of nature operate on rules completely alien to human experience. He borrowed a tool from Werner Heisenberg's work, matrices. By replacing the simple coefficients with 4x4 arrays of numbers, Dirac finally satisfied all the simultaneous equations. Applying these operators to the wave function yielded the Dirac equation. It successfully described the relativistic free electron, kept all derivatives to the first order, and treated space and time symmetrically. Because his solution relied on 4x4 matrices, the equation required a wave function with 4 distinct components. 2 of these components accidentally but flawlessly predicted the intrinsic angular momentum of an electron, mapping its spin-up and spin-down states. But the remaining 2 components held a fatal flaw. When the momentum was reduced to 0, the math demanded that electrons must possess negative energy. Dirac's quest for mathematical perfection had trapped him. He had written an elegant equation that united quantum mechanics and relativity, but it described a universe his peers were convinced was entirely fictional. Rather than abandon his work, Dirac spent 3 years defending it. To explain why observable electrons didn't fall into the negative energy abyss, he proposed that a vacuum is actually an infinite sea fully saturated with negative energy electrons, blocking anything else from dropping in. In 1931, he took the idea further. If there was a vacant hole in this sea of negative energy, that hole would manifest in physical reality as an entirely new particle, one with the exact mass of an electron, but an opposite charge, an anti-electron. The physics community largely ignored this proposal. Then in 1932, a Caltech postdoc named Carl Anderson was analyzing the tracks left by cosmic rays in a magnetic cloud chamber. This visualization shows the specific track Anderson found. It matched the exact mass of an electron, but it curved in the opposite direction, meaning it carried a positive charge. Completely by accident, Anderson had captured a positron. He had discovered antimatter. Dirac's mathematical model was correct. The theoretical deduction had successfully mapped a physical reality years before experimental tools could capture it. Over the next decade, physicists like Ernst Stueckelberg and Richard Feynman refined Dirac's theory. They proved that negative energy solutions didn't require an infinite sea. They simply represented antiparticles moving backward in time. We now know this rule applies to everything. Every single fundamental particle in existence has an exact antimatter counterpart. Because they are equal and opposite, when matter and antimatter meet, they instantly destroy each other. They annihilate, leaving behind nothing but an explosive burst of pure energy. During the Big Bang, equal amounts of matter and antimatter were generated. By the rules of Dirac's equation, all of it should have collided and annihilated, leaving an empty universe filled only with radiation. The Dirac equation predicted a universe of perfect, beautiful symmetry, but that symmetry makes our existence impossible. We only exist because that balance failed, a 1 in a billion error in the cosmic math that remains the deepest unsolved.